Right, good evening, ladies and gentlemen, and welcome to this evening's inaugural lecture in which we'll be hearing from Professor Raphael Hershey. It's a great pleasure to see you all here, and can I express a particular welcome to Raphael's family, who I know have travelled some distance to get here, so a very warm welcome to all of you. These lectures, I say every time, are a very important part of academic life here at Keele, and we very much value the opportunity to be able to showcase the prowess, the expertise of our senior academics within the university, and I'm sure this evening is going to be no different from that. It's also the opportunity to show the breadth of expertise we have here and the breadth of the impact that we have as a university, not just on the academic community, but more broadly in society at large. So it is a great pleasure to introduce Raphael this evening. He did his bachelor's and his master's degree in Lausanne in Switzerland before getting his PhD in astrophysics at the University of Geneva. He then moved to the University of Basel, where he had a postdoc job before then coming here to join us at Keele in 2007 as a Research Council UK academic fellow. He has obviously links right around the world, and that includes a position as a visiting scientist at the wonderfully named, I think, Kavli Institute for Physics and Mathematics of the Universe, and that he's had since 2008. Again, connected with those international perspectives, he has been intimately involved and indeed shown great leadership in a number of international collaborations, including an important European Research Council grant on stellar aerodynamics, nucleosynthesis and evolution. And like every good European grant, it's the acronym that makes the difference, and SHYNE is the acronym for that particular one. He has grant income of over €2 million and has written over 170 articles and given over 60 presentations in other institutes or indeed at conferences. One of the things about Raphael's work, which I'm sure we will hear about, is that he tries to adapt and address questions that on the surface to us lay people, and I should stress I'm a biologist, so I'm going to struggle with anything that's too hard this evening, but questions that sort of half sound sensible even to some of us. So, for example, how can we learn about the infancy of the universe by using stars and their supernovas as lighthouses to the rest of the universe? So that broad perspective, I think, is key, and indeed some of the work that he's done recently is leading to a whole series of new experiments within CERN, looking at some of the neutron capture on selenium, important materials and important processes. So I hope, like me, you're very much looking forward to this evening's lecture. So can I welcome to the stage, please, Raphael Hershey to deliver his inaugural lecture on using computer simulations of stars as virtual extreme physics laboratories. Raphael.
Thank you for the nice introduction. I just have to enjoy this moment. It's called all my families, friends, colleagues who have been with me, family, direct family and all. A few people who are not here, I'll mention it at the end. As Trevor mentioned, science is done in large groups, large collaborations. The names are too small for you to read, but these are not even all the people I've worked with, and I have to thank for the research I've done. Sometimes I will say I did it or we did this, and it involves a minimum of 5 people, generally many more. So I won't have time to mention all my scientific collaborators, but I'm very thankful to have great collaborators. Okay, so what is the plan? I should start by answering the question, why study stars? It will be my own version of the answer. It might not fully satisfy everyone, but I think it's important to know why we do our work. And then I will try to show you some example of how extreme stars are, how different they are from the everyday environment that we have on Earth. And then I'll show you briefly, how can we simulate stars on computers, and why is it useful to simulate stars on computers? And then once we have done this, we can then see what we can learn about stars and also how we can use stars to learn about the universe and other things around stars. And then towards the end, I will include more and more future plans. Where are we going next? What do I want to do the next 20 years or so? Okay, let's start from the beginning though. This is the church in my small village, Spherical, where I was born. If you have been in the Alps skiing, this is the Alps. This is the Lemon Lake, or Geneva Lake, as people in English call it, Geneva, Lausanne. And this is where my small village is in Switzerland. This is the farm on which I grew. That's basically the main farm building here, and then the fields will be all around. And since it's nice to see people in a different light, this is what I looked like as a child. Stress-free, happy life on the farm. But I knew it was very hard work, and I didn't have the physical energy to be a farmer. I couldn't wake up in the morning. So then I had to decide what to do with my life. And I generally have three criteria that I use, especially when there are young people in the audience. How to choose a job, how to choose a career, and I have three criteria. First one, if you can do what you like, then you'll enjoy it more, and you'll generally be better at it. Second one is, if you're good at it, it will make your work life easier, and also you'll be better at it. And the third one is it useful work? We can debate whether studying stars is useful, but if it's useful in general, then there will be a need and there'll be a job. So these are my three criteria to find a job. And I generally like sciences, so I then went on to study physics at university, as Trevor mentioned. I then moved from my small village to the nearest town, Lausanne, where there is the EPFL, which is international leading polytechnical school. Then I went down the lake to Geneva for my PhD after a brief industrial training in Japan for 1 year. And then I went very far away to the other part of Switzerland, which is the German-speaking part in Basel, to do a postdoc. So it seems like a small stretch, but actually it's a very different culture. And after that, I came to Keele. I purposely showed the Google Maps so to show that what I like about Keele is it's a bit like my village. And if anybody was around this afternoon, it even smelled like my village. So that was, I feel at home here. Okay, so I've been at Keele since 2007. Okay, let's leave Earth, planet Earth here, and go into space. And why should we study stars? Well, the first reason is the sun is our star, and it provides energy for life on Earth. Also, it is also the central object in exoplanetary systems. So when we want to study planets around other stars, we cannot understand the planets better than we understand the star in the first place. And the knowledge of star is becoming a major roadblock to planet characterization, so how to know all the details about planets. So we need to study stars in order to understand other planetary systems. Then stars play a key role in the universe. That's my one slide on the evolution of the universe. We have the Big Bang on the left, now on the right. So after about 400 million years after the Big Bang, the first stars formed and contributed to the reionization. You can see the light appearing, and they ended the dark ages. And from that point onwards, stars contributed both light, kinetic energy, and they also were chemical elements were produced. I will come back to that. And even though most stars that formed at this stage have died, we have still what are called EMP stars. That's for extremely metal-poor stars. These are low mass stars that have a lifetime longer than the time scale here, and therefore we can find the signatures of the first stars in some stars that are around in our galaxy now. And in some rare cases, we can even observe explosions of stars when the star was formed billions of years ago, but the light takes so much time to travel, we can catch a glimpse of an explosion that took place at this stage in the evolution of the universe. Okay, and then stars produce wonderful explosions called supernova explosions. In some cases, if there is fast rotation, you have bipolar jets, and they are called gamma ray bursts. And finally, the core of stars will end up into so-called stellar remnants, which are white dwarf, neutron stars, and black holes. And now for a few years, we can observe the merger of two black holes or neutron stars with gravitational waves. And I will come back to gravitational waves at the end of the talk. Okay, and also personally, stars look pretty. They come in different sizes and colors, and they're just interesting, I find. So you can see here, this is a red supergiant, very extended star. These are Wolf-Rayet stars. They have a very strong winds that are optically thick. And some extreme objects, Eta Carinae, that are not anymore spherical. Okay, finally, stars are the nuclear furnace where most chemical elements have been produced. And if you go on Wikipedia, you can find this periodic table is obviously not perfect, but it's a good start of finding out which chemical elements are produced by what type of stars. And you have, for example, hydrogen and helium were produced during the Big Bang. A lot of elements between carbon and iron group are produced in exploding massive stars, so that's supernova. And then what are called the R process in neutron star mergers, and also low mass stars will contribute to elements up to lead, for example. And this year is the year of the periodic table, so you'll hear all about the periodic table, but remember all these chemical elements were formed in stars a while ago. Okay, so let's look now at how extreme stars can be, and we start first with the temperature. So stars basically are very hot. At their surface, they have a minimum of thousands of degrees, and actually the color of a star can tell us about the temperature, and cooler stars are red, and hotter stars tend to be blue. If we go now from the surface to the center of stars, we have millions to more than 10 billion degrees in the interior, and that gets very, very hot. I really like this slide, so whenever I can show it, I take it. This is looking at the size of stars starting from planets. So we have the rocky planets from Mercury to Earth, and then we zoom out, so the Earth becomes very small compared to Jupiter. And then we zoom out again, and Jupiter is very small compared to the Sun here. And then the Sun is big compared to planets, but it's actually a small star in size. So we can compare it to Sirius, which is a nearby star. Then zoom out, Sirius is small compared to a star that were observed in historic times. So they have special names like Aldebaran. And then Aldebaran becomes small compared to Betelgeuse, which is in the Orion Nebula. And then the star that has the largest radius that we know of nearby is VY Canis Majoris, which has a radius 2,000 times the radius of the Sun. And that means that's roughly the distance between the Sun and the Earth. So you don't want to be too close to that star. And then the masses are given here. Okay, next point is about density. How dense are stars? The Sun is not too different from Earth. And the Sun, as I will explain many times, is our reference. So, and I mentioned here that the Sun is roughly 100 times the size of the Earth. A white dwarf is roughly the mass of the Sun, but the size of the Earth, so that means 1,000,000 times denser. A neutron star is a mass of the Sun by a radius of 10 kilometers, so you shrink it even more. And when gravity wins, you end up with a black hole. That's a mass more than 3 times the mass of the Sun, and a radius that is smaller than 10 kilometers. So since we're in England, I like to take the example of a teaspoon. Imagine you change your diet. You don't want to put sugar in your tea, so you're going to take a teaspoon from a neutron star. And my question is, how many cars have the same mass as a teaspoon of neutron star? So I don't know if anyone wants to guess. It will be a lot. Just giving a chance to my students. I have some of my students, I like to ask them questions. It's 100 million, okay? So if you could take a teaspoon out of a neutron star, it would be quite hard to do, but imagine you can. It's the same mass as 100 million cars using 1 ton for the mass of a car. So that shows you how dense a neutron star is, very dense. Okay, so I do computer simulations, therefore I have to show you some equations. But before I go into the details of the equations, I want to say, why do we want to simulate stars on computers? And the main reason is you can observe a star like the sun in the sky. Maybe the sun, we can observe it for 100 years if we keep records, but that's it. And stars live for millions to billions of years, so you really have only a snapshot of the star. Furthermore, you can mostly see the surface. We now have techniques like neutrinos or asteroseismology where you can probe the interior of the star, but generally you only see the surface of the star. And computer models allow us to both understand what is happening inside the star, the structure of the star, and also how it evolves with time. So that's why I'm so passionate about simulating stars on computers. So then how do we do it? Well, we won't spend half an hour on equations, but I like still to show you equations. And the first one is basically conservation of mass. Second one is Newton's law, conservation of momentum. Third one is conservation of energy. And the fourth one is energy transport. So they are the basic physics principle that you would learn in any physics context, conservation of mass, momentum, and energy. And this form is assuming spherical symmetry. So generally, if you look at the sun, it's roughly spherical. So we assume that most things have spherical symmetry. And we end up with what we call a one-dimensional model where everything is the same at a given radius. Okay, but now stars are not exactly spherical. So this is taken from the SOHO observatory, so monitoring the magnetic fields at the surface of the sun. So this is a different picture every year. So this is how the sun looked in terms of magnetic fields and solar flare over the time. So you can see that over time things change at the surface of the sun, even though the general shape is spherical. So the stars are not exactly spherical, and there's lots of physical details going on, especially magnetic fields, rotation. So in addition to the stellar structure equation that I've just briefly explained before, we need to consider a lot of interesting physics, which is very exciting for me. So we need to consider nuclear reactions, how stars lose mass by interacting with radiation. We have to consider convection and turbulence, rotation, magnetic fields, interaction with the companion if two stars are close by, and then things like equation of state, opacities, and neutrinos. Okay, so now we are ready we know what physics we want to include in the model. The next question is, how many dimensions do we consider? I said we started with 1D spherical symmetric model, but stars are 3D objects, and processes like magnetic fields and rotation are multi-D. So ideally, in my dreams, I simulate stars on computers in 3D. The problem is 3D is very expensive. You will see an example in a minute. But the main advantages of 3D is you can fully simulate everything in full 3D, follow magnetic fields going crazy in all directions, axial rotation, asphericities on the star. So that's how we would like to do it. However, the cost is so high that we can only simulate about 1 second to a few days of the lifetime of the star, when again, the lifetime of stars is millions to billions of years. So we'll never be able to simulate the entire life of stars in 3D. We can generally also never resolve the large scale, which are seen in such simulations, and the small scale where, you, for example, you have processes like viscosity. So we're missing important things if we are interested in the entire lifetime of the evolution of stars. So then we go generally to 1D model. So like stars, we can approximate a cow, especially if the cow has eaten lots of grass, as a spherical object. And then we say, okay, it's roughly spherically symmetric. And then the main advantages then become we can simulate the entire evolution of the star, and we can follow stars with different initial parameters, so different initial mass composition, and do lots and lots of models as we want to do. Obviously, the disadvantages are then that we have to use parametrized physics. We are missing multi-D process. So in the case of the cow, for example, we know the cow has horns, and the horns on the head are not spherically symmetric. So we have to find a way to improve our 1D model to take into account, for example, for the horns, the effective effect of the cow having horns and not being perfectly spherically symmetric. Okay, and then the way forward will be to simulate stars in 1D, find out what are the major uncertainties and problems with the 1D models, go to 3D targeted simulations, and then go back and improve our 1D models and go around this circle several times. So let's start now by looking at some 1D models. So this is the code I've used most of my time of my scientific career. Is I would call 1.5D stellar evolution code. The 1.5 means that we relax the assumption of spherical symmetry. So for example, if a star rotates along this axis, the equators gets elongated, so we have an oblate shape. And this is taken into account by correction factors in our typical 1D equation. So this is, for example, an energy conservation equation that I've shown before. And my PhD supervisors, André Médé and Georges Médé, did all the work, so I could just step in and benefit from their work. And the key thing is they managed to keep the equations 1D by assuming some effective and averages over what we call isobars. And these grids of models are very popular and very useful for the community. So these two papers and a few more have gathered roughly 1,000 citations in 6 or 7 years. So we can see how useful and how much demand there is for these models. Okay, so now that we have computer models, we can learn about stars, their structure, how they evolve. If you remember one thing from tonight, you have to remember that the mass is the key property of a star. It will determine its structure, is how it evolves, how long it's going to last, and how it's going to die. So the mass is the key reference, and the sun being our main star, we're going to use the solar mass, so this symbol 1 solar mass, as our reference, and we're going to describe all stars according to their initial mass with respect to the sun. And other properties are initial composition, so that is what distribution of chemical elements are in the star when the star forms. So shortly after the Big Bang, you only have hydrogen and helium. And then nowadays, you have lots of elements that we know from the periodic table. So that will also affect how the star evolves. Then, obviously, different stars will have different rotation rates. And also, they can either be single or with companion. Sometimes they split up. Sometimes they merge. So lots of things happening. OK, so let's look at the evolution of a star like the sun. So the sun is a 1 solar mass star, obviously. The sun is currently burning hydrogen. It's a middle-aged star. It's about 4.5 billion years old. It's got another 4.5 billion years to burn hydrogen. And that's kind of the information that it's quite useful to know how long the sun will stay in the same state if we want to know how long we have to live on Earth. All right, so we still have a lot of time, another 4.5 billion years before things change. At that point, it will be time to find another Earth, because the core will contract, and then as a result of this core contraction, the envelope will extend, and the sun will be almost as large as the largest stars we've talked about, and the radiation will just kill any life on Earth. So in 4.5 billion years, it's time to go. Until then, the Earth is our only home, so we have to look after the Earth. And Keele has a strong program in sustainable futures, and that's very good. Okay, so then in 4.5 billion years, the sun will be called a red giant star, and this is the structure it will have. And then what happens next is we have helium burning into carbon and oxygen, and after that, the core becomes a white dwarf, as I introduced white dwarf before, and then stellar winds, as we call them, will blow away the outer layers, and the white dwarfs are very hot, so they have very high energy light that will light up these what we call planetary nebulae and make for very nice pictures. So that's how the sun will end up in about 5.5 billion years, so after hydrogen and helium burning. I study most of the time massive stars. So massive stars start their life like low mass stars. They burn hydrogen into helium, and then helium into carbon and oxygen. But then as they keep contracting, their core gets hot enough to burn more species. So the next one is carbon is going to burn. We're going to have carbon fusion burning into elements like neon and magnesium. Then neon is destroyed by the heat into oxygen and magnesium. Then we have oxygen fusion producing elements like silicon and sulfur. And finally, we have silicon and sulfur either being destroyed or capturing alpha particles so that we end up with nickel-56 and other ion group elements. At this point, ion group elements being the most stable elements in the periodic table, there's not enough nuclear energy generation to counterbalance gravitational contraction. So at this point, we have an ion core that will collapse. It will reach nuclear densities in the center, so that's where the strong nuclear force will prevent any further contraction. The additional infalling material will bounce and then start a shock wave that will produce the supernova explosion. That was stellar evolution and supernova explosion in 1 minute. Okay. So then we end up with more pretty pictures. This is the Crab Nebula, exploded in 1054 and observed by Chinese. And then we have different types of supernova according to whether there's hydrogen or not in the spectra. And then one note is that type 1a supernova come from low mass stars like the sun, accreting from a companion. And most supernova type come from massive stars after going to the ion core collapse. Okay, so now I want to present a few highlights from my work. I think I'm just on time, that's perfect. So what do we want to learn about stars, and how can we use stars to learn about the rest of the universe? So the one question I always wanted to ask is how massive stars can be. So I will address this question. How to improve 1D models with 3D hydro simulations? What type of supernova can we expect? And since we are now able to observe gravitational waves, we want to know what kind of signal we can expect to get, and what can we learn about stars from these mergers. And then I will talk also about how we can use chemical elements as tracers, as forensic evidence of the evolution of the universe. Okay, the first one is how massive stars can be. In particular, now you might say, well, do we care about stars more massive than 100 times the mass of the sun? Well, there are special types of explosions that would occur only if you have about a few hundred solar masses. So those are called pair-instability supernova. They're extremely powerful. They produce a lot of iron. So people want to know whether this type of supernova exists. But the first requirement is that you form a star that is massive enough to get into that range. Because if you look at star formation, as the stars form, they start to radiate energy. And at some point, the radiation will be stronger and push away any material that comes onto the star. So for decades and decades, scientists would say you can't form a star more massive than 30 times the mass of the sun, because the radiation from the star itself, the protostar, will blow away any gas around it. But the latest simulations have shown that you can accrete along the equator and have luminosity or light escaping along the poles. And therefore, you can build a very massive stars. In our calculations, it's possible to simulate stars that are 1,000 times the mass of the sun. Some have used up to 100,000 times the mass of the sun. And obviously, it depends what physical ingredients you put in the model, because the computers only do what we tell the computers to do. So maybe we are missing some physics. Assuming they exist, can we see them? Because massive stars burn their fuel faster, therefore they are short-lived, and they are very rare because of a distribution function. So they're rare and short-lived. So what people had to do is to look at the youngest and most massive group of stars. And for many years, everyone, including myself, thought that the maximum mass would be around 150 times the mass of the sun. And there are very good reasons. I will come back to the Eddington limit on the next slide. But that's the point where radiation pressure is stronger than gravity. And you expect not to have stars above that point. But some colleagues were bold, and they looked at in the right place. This is the R136 cluster in the Large Managing Cloud. This is the zoom up. This is the cluster. In particular, the star A1 is now the record holder for the most massive star. It has a current mass of 260 times the mass of the sun and had a birth mass of 320. So it's nice to be a very massive star. You just lose mass and weight as you go along. And their secret is they live a fast and furious life. I'm not sure this is good for us, but you could try, you don't know. Okay. And obviously, the secret is to work, to do computer simulations and compare to observations. So Paul Crowther and his team did the observations, and they asked us for models. We compared their observations to our models, and then end up with these numbers. Okay, and very massive stars are also very luminous. The reason why we think this star is so massive is because it has a luminosity that is 10 million times the luminosity of our sun. And alone, it supplies 7% of the ionizing flux of an entire region. For those who know the 30 radius, it's a very big region with lots of stars, and this single star supplies 7% of the ionizing radiation in that region of space. And as part of studying these very massive stars, using our models, we can then explore the dependencies between, for example, luminosity and mass of the star. Because if you look at most textbooks, even astronomy textbooks, you'll know that a luminosity of a star is proportional to the cube of the mass, and that's very valid for stars in, like our sun. But as you go up in mass, the structure changes, and therefore this is the luminosity versus initial mass. The curve flattens, and therefore the luminosity is roughly proportional to the mass. And this is key when we compare the radiative force, which is proportional to L, to gravity, which depends on M. And if these two are equal or just proportional, as they increase, gravity can always stop the radiation pressure of evaporating the star. So that fact removes the argument of the Eddington limit on how massive stars can be. Okay, I won't describe this slide in detail, but this is just to highlight an example where we can predict properties of stars and also of the early universe by comparing models to observations. I've introduced the topic of extremely metal poor stars. So these are low-mass stars that are so old that they were formed when the universe was less than 1 billion years old, and they're still around today because they just evolved very slowly. And what is puzzling about them is that they have a strong strontium over barium ratio that people could not explain before. And that shows us how using chemical elements is a powerful tool. So we have the observations we wanted to reproduce as black dots here. We ignore the blue dots for now. And by using stellar evolution models that we calculated and some more modeling of how if you produce chemical elements inside the star is distributed in the what we call interstellar medium, goes into the galaxy, we form the next generation stars. So they're called galactic chemical evolution models, which are shown in orange and red color. We could see that by adding the effects of rotation in our models, we could very well explain not only the range of observation, but also the scatter in the observation. So that was a big success. There was a paper in Nature in 2011, and then lots of follow-up studies. Okay, now I want to talk about what was the core topic of the SHYNE ERC project. As Travis said, I was quite happy with the acronym. SHYNE sounds very good. Project was also good. So this was a 1.4 million euro project. It ran for 5 years, so now it's finished, but there'll be another one. Okay, and the main goal was to improve 1D models with 3D hydro simulations. So now we're going to look at 3D hydro simulations. Okay, and I said that 3D hydro simulations are quite expensive. So 1D model I've talked about would take a day to a week if you're very slow or you want to calculate lots of things, 1 month at most. But actually, if you want to calculate 3D hydro simulations, you need millions to billions of computing hours. And the simulation you will see in this talk would have taken 85 years on this laptop, which is already quite powerful, right? It would have taken 85 years. But instead, because we could use supercomputers in Durham, we only took a few months. And I will show you later a simulation that used 40 million hours in a computer system in Barcelona. So these simulations were done with the Prompt code developed by Casey Mikin and David Arnett, with whom we collaborate. And the idea is we target a specific part of the star, which is this cube. This is where we have carbon fusion. So we have carbon fusion here. And this is called box in a star, So we just put a cube inside the star and only going to simulate this for a short while. Okay, and the movie is basically a vertical snapshot through that simulation cube. So this is the simulation cube. There's carbon fusion at the bottom here. It heats up the material, the gas above it, and causes turbulence in this region. And we know it's supposed to stop roughly there from the 1D stellar evolution calculations. And this is where carbon burning occurs. If in that vertical snapshot, this is where the 1D models would tell us the mixing stops. So these are called radiative regions here on top and below, and convective region in the middle. Okay. And if we have the spherical symmetry assumption, then basically the 1D boundaries are straight lines. And now we can see in 3D hydro simulations, are these lines really straight, or how much do we deviate from that picture? So this is the animation. So as I said, this simulation took a few months on a computer system in Durham. And then we have carbon fusion heating up the material, so if you can follow the mass flowing. What is shown is actually the velocity. The color is the velocity, so red is fast motion, but you can kind of see how the material goes around that region. And if we compare to the 1D picture, which is again the straight line, we can see that the boundary is actually not straight. It undulates because it's being pushed from below, so it wobbles. And also there's what we call Kelvin-Helmholtz, which is shear instability when you have friction or flows at the boundary. So we were very happy with this. We have very pretty movies to show. But this was, in a way, the easier part. Now we are left with the harder part, which we have started doing, is we then have to translate these results back into 1D type of results. And for this, we need to use theory. So I won't describe how we do it in detail, but just mention a few keywords, which is called Reynolds average Navier-Stokes analysis framework, or we also call it ELS, RILS, and it's basically using horizontal averages and temporal averages of our 3D results to go back into the 1D model. And skipping all the details, this is our, well, I'm very proud of this result, is this is the entrainment velocity. So how fast does the boundary move out, being pushed by turbulent motion, normalized by turbulent speed, as a function of the stiffness of the boundary. So if you have a high number here, the boundary is very stiff, so you're going to have to push it very hard. And here, the colored points are results of our computer simulations, and the black solid lines is the theory of entrainment law. So what our results, numerical simulation, confirm is that our simulations really follow this theory. And when you have a theory that works for your case, that means you can apply this theory to all stars of all masses and throughout the evolution, not just during the snapshot that we simulated. And here we varied very different things. So we varied the strength of the turbulence, so how fast things move, and then the bottom boundary is stiffer than the upper boundary. So there are very good reasons for these points not to lie on the same line. Okay? It's almost too good to be true, but reality always is there. So these are different simulations for oxygen burning rather than carbon burning, and we see that they don't agree perfectly. So there's more to be learned. But this is a very important result because it's not just result for one case. It fits into a theory, and we can use now this theory to improve our 1D models and then calculate lots of models for lots of stars. Okay, so where do we go next in this situation? I said we have done carbon burning. People have done oxygen burning, so we need to do more different burning stages. And Cyril George in Geneva is simulated on the PRACE system. So this is, if you've not seen the picture, it's like a supercomputer inside the church in Barcelona. So it looks very pretty. Very happy to have gotten. So we had 40 million computing hours to spend in 12 months. So it was quite busy to just keep the simulations running. And another student, Leo Horst, is doing helium burning with a different code. He's working in Germany. Okay, but how can we generally go further? Because millions of CPU hours is not enough. We need billions so that we can consider larger fraction of the star or longer time scale. And in order to do that, we need to use GPUs. And for example, the largest systems on the planet start to be equipped with GPU. There's a Swiss computer system. We're in the top 10. And the reason why it's in the top 10 is because it's using graphical processing units. This is hardware developed for gamers, but we can also use them for computation. And it's not so easy to learn how to use these. So we thought it would be good to have our own system to learn how to use it. And we've named the system LIGO. So Laura suggested the name. And anyone knows what a LIGO is? It's a hybrid between a tiger and lion. You might have guessed this. Well, I don't know if you've seen a picture of a LIGO. This is a picture of a LIGO. It's basically more powerful than either a lion or tiger. And the idea behind hybrid computing is you have a stronger system by combining the strength of different systems. So it's extra powerful and large. So this is our prototype. This is the smallest supercomputer that you can build. You need a head node that stores all the information. These are hard disk spaces, so you can store the data. And this top part tells the other computers what to do, how to do the work. So it's called master. And these are called slaves because they do most of the work. And in this one, you have just standard CPUs. So these are 2 CPU units. While in the bottom part, each computer box contains this NVIDIA P100 GPU chip or hardware. And the idea is we can then develop our code to work on multiple GPU cards. And once our code is running on this small system, we can then apply for billions of computing hours on the supercomputer in the planet, so in the US or Switzerland. Okay, that brings us to collaboration with industry. I'm very passionate about collaborating with industry. Now you might think, what do stars have in common with industry? Generally nothing. So I have to fight hard to find ways to collaborate with industry. But it's basically by doing computer simulations, I want to get the most out of computer systems. And by working with people who develop computers, I can get more out of the computers. And an example, I collaborated as part of the ERC project with a Norwegian company called Numascale. And by working with them, we could get very good results for nuclear physics. And then one experiment at CERN, as Trevor mentioned, followed from our theoretical work. Okay, and in general, it's very difficult to work with industry. But for the industrial partners, they can have some R&D done for free. And also, it can help with the recruitment. As I said, for academic people, we can have the edge over academic competitors. And also, we can improve career prospects for our current students, and especially PhD students. Okay. So after the SHYNE project almost finished, just before that, we started COST Action. So this one is named ChETEC, not as fancy as SHYNE, but we can't have always the perfect name. ChETEC, though, stands for Chemical Elements as Traces of the Evolution of the Cosmos. It kind of goes around everything that I've mentioned before in terms of science. We basically work with nuclear physicists who do theory or experiment, people doing astronomical observations, and then people doing various types of modeling of stars and galaxies. We all work together. We also collaborate with the industrial partners to try to answer some of the open questions in astrophysics. This is a big network that's funding for traveling mostly. So we have 30 European countries involved. So you have a full list here. So I get to visit lots of European countries now often. And we're also cooperating with the US counterpart called GINA-CE, which is the Joint Institute for Nuclear Astrophysics. And the idea is now they're applying for a scheme called Network of Networks. So that's joining efforts or cooperation between the US and Europe so that we solve scientific problems together. So it's very exciting to have a worldwide cooperation on our topic, research topic. Okay, last brief topic of today, I think, just one or 2 minutes, is gravitational wave astronomy. The last few years, we have been able to observe the merger of compact objects. And basically, gravitational waves is the warping of space-time when objects are accelerated, so very dense objects. So that's why we observe neutron stars and black holes. And it's a bit faint, but this is like the current stellar graveyard of known neutron stars with masses up to about 2 solar masses, and black holes above 5 solar masses. And the systems in blue here have all been observed by LIGO. So that's the gravitational wave observatory. So what we can learn about with gravitational waves is the masses of black holes. And as they call black, generally we don't see them. We see them sometimes, but we see a lot more now. So we can study like the mass distribution of black holes or how massive black holes can be. And therefore, this links back to stellar evolution, because the end point of evolution of stars is to produce black holes. So I'm going to get more and more involved in gravitational wave progenitors. Okay, so to conclude, stars are important and exciting objects. They are full of interesting extreme physics, nuclear reactions, convection, rotation, magnetic fields. We need a combination and synergy between 1D and 3D models to be able to understand stars, predict their fate, their structure. And we have exciting times ahead because we can explore complex physics in unprecedented details by using the combined power of GPU and CPU. We have global collaboration tackling the open questions, and gravitational wave astronomy is now around, so we can learn more and be excited about it. So thank you for your patience. Oh, sorry. Sorry, I just forgot. I forgot to thank my family, friends, and colleagues for the support over the years. So not all of them are here, but a small group is there. And okay, thank you.